Okay, well, let's get started. Apologies again for the technical difficulties. Everybody's having a lot of fun dealing with Zoom these days. So, welcome to tonight's edition of Cosmos from Your Couch, presented by the Dunlap Institute for Astronomy and Astrophysics at the University of Toronto. My name is Patrick Bracey. I am a postdoctoral fellow at the Canadian Institute for Theoretical Astrophysics, and tonight I am going to tell you a brief history of everything. So like I said, I work at the Canadian Institute for Theoretical Astrophysics, which I like to think of as a more academic-y way of saying the Canadian Institute for Thinking About Space. And my particular brand of thinking about space is that I am a cosmologist. Now, for those who don't know, a cosmologist, cosmology is the professional skill or practice of, that's cosmetology. That's a totally different thing. A cosmology is the branch of astronomy that deals with the origin and structure of the universe. We study the universe as a whole, not necessarily looking at any one planet or star or any single object in the universe, but trying to understand the whole story of how the universe was formed and how it grew and evolved to be the way it is today, and what's going to happen to it in the future. So my goal for tonight is to cram 14 billion years, 14 followed by 9 zeros of cosmic history into the next 30 or 40 minutes. So we will see how that goes. It's going to be a little bit of compression. Now, there's only one place you can start a story like that. So, in the beginning, there was something. I have no idea what it was, and neither does anybody else. See, I have a small confession to make. Despite being a cosmologist, I hate the name The Big Bang Theory. Now, not because it's kind of a silly name for the beginning of literally everything, and not for reasons having to do with Sheldons of any age, but because, cosmologists like me have spent the last several hundred years trying to figure out how the universe got to be the way it is today. And we have done a fantastic job figuring out just about every part of that story, literally every part of that story except the Big Bang. The Big Bang is the part of the story that we understand the least, and yet it's the thing we named the whole process after. The Big Bang Theory is, in a very literal sense, a theory of everything in cosmic history except the Big Bang. So how did we end up in this situation? How did we actually figure out as much as we do know about the universe? And why did we get stuck with this name, the Big Bang Theory? Well, I'm going to start by telling you a little bit about two astronomers from the early 20th century. One you might have heard of, Edwin Hubble. He's a rather famous guy. We named a multi-billion-dollar space telescope after him. That's probably the single most famous telescope on Earth. So Hubble's got a good amount of publicity. The other person I want to talk about is an astronomer called Henrietta Swan Leavitt, who you might not have heard of, probably in large part to the fact that we're generally not very good about recognizing the contributions of women to the history of astronomy. But moving aside from this, in the early 20th century, around the time these two were operating, this is more or less what we thought the universe looked like. We had us here on Earth, right in the middle of everything where we belong, and there were, maybe a few thousand stars around us scattered around in kind of a vaguely disc-like shaped, and this was all that is and all that ever was. And the prevailing scientific thought at the time was that this universe was static. That our nice little pancake of stars had existed more or less the same way for all of eternity and would continue to do the same until the end of time, which time didn't have an end, so until forever. But there were some mysteries at the time, and one particular one, called the Great Debate, centered around these things that they called spiral nebulae, because weird swirly thing doesn't sound sciencey enough. Now, this is an actual picture taken in, I believe it was 1910, through one of the telescopes at the time. This is a picture of some, spiral-shaped formation that you could see out in space. Now, nobody really knew what these things were, and that's in large part due to a pretty fundamental problem in all of astronomy. And that problem is, if I'm looking at something out in space, and I don't already know what that thing is, then something that's relatively small and close to us and something that's very large and very far away from us will look exactly the same through a telescope. So in order to figure out how big something is, you have to figure out how far away it is. But you can't figure out how far away it is easily because you don't know how big it is. And so the big contribution that Henrietta Swan Leavitt made was this was the first one to figure out a way to measure, one of the most important ways we use to measure distance in astronomy. Brace for slightly jargony couple of slides. I apologize in advance. Henrietta Swan Leavitt studied these special kind of stars we call Cepheid variables. Now, most stars, you look at them, they're more or less this, their brightness doesn't really change much over time. But these Cepheid stars had this weird property where they would start out faint, then very quickly get much brighter, and then slowly decrease in brightness again before repeating. And this would happen very regularly over a period of a few days. Now, these had been known for a while, but what Leavitt figured out is that the period of this pulse, the amount of time it takes for the star to get bright, dim down again, and then get bright again, gets longer the brighter the star is. So if I'm looking at one of these stars pulsing, if I look at how fast it's pulsing, I can tell how bright it is. And if I know how bright it is, just like how big things look smaller when they're farther away, bright things look fainter when they're farther away. A flashlight looks very different across the room than when somebody's shining it straight in your eye. And so what this does is if you find one of these Cepheid stars and measure how fast it's blinking on and off, you can tell exactly how far away it is. And so what Hubble did is Hubble found some of these Cepheid stars in some of these spiral nebulae. And what he figured out by looking at them is that these are not small little clouds of gas within our little pancake of stars, that these are unbelievably immense structures that are incredibly far away. And these are what we now call galaxies. Also, still, because weird swirly thing doesn't sound sciencey enough. So the closest big galaxy to us is called Andromeda, or M31 to give it the cool kid's name. Andromeda is roughly 24,000 million, billion, trillion, quadrillion, quintillion kilometers away. Now, that is an absurdly large distance. Your brain has no idea how far 24 quintillion kilometers is, and neither does mine. Those numbers are just too large to make any kind of sense on human length scales. I can try to do, there's a thing astronomers love to do where they try and make an analogy where I say, like, okay, if the Earth was the size of an egg, say, well, then the Andromeda Galaxy on that scale would be 94 billion kilometers away, which is still too big of a number for anybody to get their heads around. And at some point, you just kind of have to throw up your hands and say space is just incomprehensibly vast, and there is just no way the human mind can actually manage to take that in. If nothing else, astronomy is very good at telling you you are not special in billion-mile-high flaming letters. But just to give you an idea of just how big these galaxies are, if I look at Andromeda, which is, like I said, 24 quintillion kilometers away, if it was bright enough to see with the naked eye, it would be about 6 times the size of the moon on the sky. This is an actual size picture of Andromeda in the typical night sky on Earth. And that, to me, is just absurd. We go from the universe being, a modest-sized pancake of stars to, nope, sorry, our little star cluster around us is an incredibly tiny fraction of the universe. We are not even at the center of our own galaxy. We're actually about halfway out to the edge. And our galaxy is just one of hundreds of billions of others that are just as big. And now that just starts to be too much for the average person to handle. Heck, not even the average person, even the average astronomer to handle, to be perfectly honest. Now, that wasn't all Hubble did to get his name on all the fancy telescopes. See, when Hubble was looking at these newly named galaxies and measuring their distances, he figured out something even weirder about them. See, just about every galaxy Hubble could see through his telescope turned out to be moving away from us. And the farther away those galaxies are, the faster they're moving away. So maybe you say, okay, maybe there was some big explosion in our Milky Way galaxy that threw all of the other stuff in space out away from us. Or maybe the other galaxies just think we smell bad or something. But if you do a little bit of geometry, and us science types are pretty good at geometry, you can figure out that if we were sitting in any of those other galaxies, the picture would look exactly the same. It would look like every galaxy in the universe was moving away from us. Now, that's weird enough on its own, but then let's go one step farther. If every galaxy in the universe is moving away from us, then what happens if we look at the universe on rewind? Bow before my fantastic PowerPoint animation skills. If everything is moving away from us now, then it follows from that at some point far enough in the past, everything must have been in one place. And that event where something took the universe from being compressed into an incredibly small volume and threw all of the matter in the galaxy so fast that we're still seeing it moving away from us 14 billion years later, that event, whatever it was, is what we call the Big Bang. Now, as to why we're stuck with that name, well, probably because if we called it nobody's going to make a TV sitcom called the Lambda CDM cosmological model. So we're kind of stuck with that name. So all of this has been a very roundabout way of telling you that I can't actually give you much detail about how the universe actually began, because we don't honestly know. It's something we're still trying to figure out. However, I can instead start the story shortly after the beginning, when the universe looked like this. Now, you might think, I've seen, pictures from that telescope we named Hubble after. I've seen all sorts of pictures from space. Heck, you've been showing me a bunch. The universe looks like this. It has all of these galaxies you've been talking about and stars, and it's mostly empty. How does the universe go from, a blank white void to all of this? Well, at this point, the reason why the universe looks like this is the universe is basically one single cloud of hot hydrogen gas. And it's so hot that it's glowing white hot. Actually, at some point, it's glowing X-ray hot, which is much hotter than white hot. But just like a piece of metal that comes out of a forge glows from its own heat. Now, it doesn't look like much, but if I turn the contrast on this picture up a bit, you'll start to see something emerging. So what you're seeing here is a map of the universe roughly 100,000 years after the Big Bang. Now, and what you're seeing is false color, but the red blotches here are places where that light from the hot hydrogen gas is a little bit brighter than its surroundings. And the blue places are places where it's a little bit fainter. It's places where the gas is a little bit warmer in the red spots or colder in the blue spots. Now, what this actually is this is a picture of the universe when it was only 100,000 years old. Now, 100,000 years might not sound like something that would normally get the term only applied to it, but since the universe is 14 billion years old, 100,000 years is nothing on the timescale of a universe. This is basically a baby picture of the universe. Now, you might say, how can you possibly know what the universe looked like as a baby? You're secretly hiding a time machine or something? And it turns out we are, but it's not particularly secret. See, every telescope on Earth is, in a very real sense, a time machine. Now, not one that can actually take us back in time, but one that allows us to look back in time. It all comes back to the fact that the speed of light is not instantaneous. Light travels at a constant speed, and that speed is what we call, tautologically, the speed of light. That happens to be about 300,000 kilometers a second, or 186,000 miles a second for my fellow Americans. And what that means that when I see anything using light, and we see everything using light, I'm not seeing it as it is now, I'm seeing it the way it is when the light left. So for example, the moon, it takes light about a little over a second to get from the moon to us. So when you look at the moon, you're looking a second back in time. The sun, well, it takes light about 8 minutes to get to us from the sun. So if the sun were to magically disappear right now, nobody on Earth would know anything about it for 8 whole minutes. The nearest star to us, a star called Alpha Centauri, it takes light about 4 years to get there from us. And this is in fact where we get the term light years from. A light year is the distance that light travels in a year. So if light takes 4 years to get to us from Alpha Centauri, that means that Alpha Centauri is 4 light years away, and that we are looking 4 years into the past when we look at Alpha Centauri. Now, how about Andromeda? Andromeda, it takes like 2.5 million years to get to us. So when we look at Andromeda, we look 2.5 million years back in time. So all we have to do is we point our telescopes out behind all of the stars and galaxies we see in the universe and look at the most distant light we can see. We see, using a telescope we call the Planck satellite, which a number of people at the University of Toronto worked on, we see this pattern of bright and dark spots, and we know that it's coming from when the universe had barely been born. Now, when I say these spots are a little bit brighter or a little bit fainter than their surroundings, I really do mean a little bit. We're talking a factor of 1/10,000th separating the bright spots from the cold spots in this picture. You know, you don't get super excited if you go into a store and see a bunch of signs saying 0.001% off, but it's enough to matter. And the reason why that matters ties deeply into how we actually get all of the galaxies we look at in the universe. Because these cold spots, these blue spots in this picture, these are places where there's a little bit more stuff, where there's a little bit more hydrogen, a little bit more matter. And the red spots are places where there's a little bit less. So if we follow this, the history of the universe and let this light, this cloud of hydrogen gas evolve, well, the light we're seeing from it pretty quickly fades out. It gets fainter and fainter and redder as the universe cools, to the point where the universe looks to what would be a human naked eye, if any existed, like this. This is now a period which we have creatively termed the Dark Ages, because it's the age when it was dark. But there's something really important happening here. All of those places where there's a little bit more stuff are starting to suck in their surrounding matter because they have a little bit more gravity. And as they pull in more matter, that gravity gets stronger and the process accelerates. So we can run computer simulations of what this process is looking like, even during a period where we can't actually see anything. So what you're seeing here is these bright blue spots are places where more and more material is being pulled into. And these red spots are developing are enormous voids in this gas cloud that is the universe, places where there's like not even a single hydrogen atom for light years at a time. And you can see this process continues, and these overdense regions become denser and denser, and these large voids become larger and larger as all of their gas is sucked down onto the dense regions around them. And this was just a computer simulation, but we can see the end result of this in the real universe. What I'm showing you now is a map of the nearby universe. So we're sitting down here at the bottom of this cone, pointing our telescope out into space, and every single dot of color in this picture is the location of a galaxy. Remember, one of those incomprehensibly large, incomprehensibly far away object. This is a map of millions of those. And this is not the edge of the universe or anything like this. This is just as far out as we could see with the telescope they used to make this map. Now, you can see if you look at this, the positions of the galaxies aren't random. There's this kind of web-like pattern to it. And in fact, it's a very similar kind of web-like pattern to what I showed you in that computer simulation. And that's because the densest regions, the densest places, the places here where, there was 1/1000th of a percent more material than in their surroundings, those places were what sucked in the most mass, and galaxies form in those densest regions. So we can draw a direct line from this baby picture of the universe just through gravitational evolution down to this map of the universe that we see today. All just from these, initial very tiny little blotches collapsing down to these immense galactic scale structures. And that is, kind of a remarkable triumph of science, that we're able to cover such an immensely huge area of space and such an immensely long span of time with such a simple theory. It's honestly one of my favorite things about doing this job. My lovely assistant, my wife Heather, has indicated there's a question in the YouTube chat. So there's a question from Sharon Edelstein saying that if we only know how far light is away using a special type of star, how do we know how far away and how much time has passed since this map that I showed you? So any talk about astronomy, whether to the public or to fellow astronomers, will always lie a little bit, will always make things simpler because, it takes several years of education to learn all the details about this stuff. The special kind of star isn't the only trick we have right now for measuring how far away things are. There is this particular light that we're seeing from just after the Big Bang, there's a very special property of it where the amount it gets fainter scales very precisely with how much time has passed. So if we measure how bright this light is now, and we know from some pretty sophisticated math how bright it should have been right after the Big Bang, then we can measure how much time has passed since then. There's a famous satellite called COBE, which first made this measurement in the mid-90s and won a Nobel Prize for it. But we have lots and lots of other tricks now for figuring out how far away things are. The Cepheids were just the key to figure out that particular issue with the spiral nebulae. So to continue, we've so far traced the history of the universe from this, small fluctuations at almost the very beginning of time down to this cosmic web of galaxies at the present day. But if you think about what I've said so far, and you remember that we're looking at galaxies, you might notice that there's parts of the story that are missing. Most notably, I said, we couldn't watch the fluctuations in the universe grow under their own gravity, that was taking place in the dark ages. Well, something very important about galaxies, they're not dark. We can actually see them. And the reason why we can see them is because this collapse process doesn't stop when you've made galaxies. It doesn't just say, okay, we made a cool spirally shape, we're done. It continues. Inside the collapsing gas, there are still pockets where there is more gas than their surroundings. And a lot of those places are these things we call nebulas. This is the Orion Nebula. It's one of the most famous, and you can actually see it with the naked eye on a good night, just under Orion's belt. These are places where the kind of diffuse gas that fills in the space between stars has continued collapsing on its own gravity to produce these beautiful clouds that we see out in space. But the process doesn't stop there. Inside those nebulas, that collapse is continuing. It's still not perfect. So this is another computer simulation, only instead of trying to model the whole universe, now I'm only modeling a single cloud. And again, And again, these bright patches are places where there is more gas, and that gas is pulling in more matter from its surroundings. We're just zooming in a little bit on it now. And if you look closely, you'll start to see these little white dots appearing in this image. Something very special happens when the gas collapses down to a certain scale. See, at some point, all of that hydrogen gas in the universe starts being squeezed tightly together enough that individual hydrogen atoms combine together to make helium atoms. Now, we on Earth have figured out how to squeeze hydrogen atoms together and to make helium. And when we do that, we get nuclear weapons. That's why the biggest nuclear bombs are called hydrogen bombs, because this fusion of hydrogen atoms releases a lot of energy. And so far, the main use we found for that is using it to destroy, unfortunately, large amounts of things. But when the universe, when these big nebulae collapse far enough down to squeeze hydrogen atoms together, that's where we get stars. A star is basically a continuous nuclear explosion where the energy from all of these hydrogen fusions happening in the very center of the star finally provides enough energy, finally provides enough force to stop the gravitational collapse that has been going on since the beginning of the universe. So these nebula, these clouds of gas, these are the birthplaces of new stars. And those stars don't just stop with making hydrogen into helium, but as they evolve, they start condensing helium down into other elements like carbon and nitrogen and the oxygen we breathe. And when those stars die, they make even more elements. And sometimes when the remnants left over from those stars crash into each other, they make even more. And so ultimately, all of the elements in the universe heavier than hydrogen and helium, and maybe a little bit of lithium, are formed from this gravitational collapse that makes stars. Everything around, there's a famous Carl Sagan's quote that we are made of star stuff. We are, all of us, our planet and everything we see around us is literally made from elements that were produced in these stars, which were formed in this collapse that had been ongoing from the beginning of the universe. But as I've said 3 or 4 times already, the process still doesn't stop there. This process of collapsing the whole universe down into individual little stars isn't quite perfect. If we look closely at a bunch of the newborn stars in this Orion Nebula, we see this kind of black fuzz around them. And what this is leftover material that didn't quite, got pulled into the gravity of the forming star, but it didn't quite manage to get sucked down onto the star itself. Now, you could probably guess what these turn into when I tell you that they're called protoplanetary disks. Astronomers, again, are not particularly creative with naming things. And that means that inside these disks, just like at every other level I've been talking about, there are bits of the disk where there's more stuff than their surroundings, and those bits will pull in more and more of that black fuzzy stuff, and eventually that's where we get planets. Big planets, small planets, and eventually in orbiting around a rather otherwise unremarkable yellow star about halfway out the Milky Way galaxy, one of those planets had the right conditions for liquid water, and eventually to evolve life, and eventually TV sitcoms named after cosmological models. And so this whole process from the Big Bang to the Big Bang theory is driven to an astonishing degree by this simple process of gravitational collapse, of places where there is more stuff pulling in more and more things from their surroundings, and eventually making more and more complicated objects and all of the structure we see in the universe today. So I will pause again for another moment to ask if there are any other questions from the chat. And I will have to pause for slightly longer because there's about a 30-second delay between me talking and it showing up on your YouTube. So I will just kind of awkwardly sit here for a minute and be glared at by my cat because I haven't fed her yet. Okay, well, I will continue on, and my wife will flag me down if there are any other particularly interesting questions. So, I've gone through a pretty quick but not bad summary of what we know of the history of the universe so far. What I want to talk a little bit about now is what don't we know? In other words, why do I have a job? What are we still trying to figure out? So the first thing I want to bring up is, I mentioned that we can simulate the gravitational collapse of these initial fluctuations in the universe down to this cosmic web structure, but the patterns don't look quite right. If we try and do some math at these things, try and count up like how many big blobs do we expect versus how many small blobs do we expect. If we try to predict what that looks like for a universe that's just made of hydrogen gas, well, this graph, which again, you don't have to worry too much about what this graph is actually showing. These red dots are what we measure actually looking at the actual blobs in the universe, actually counting the number of galaxies. This blue line is what you would predict if the universe was only made of hydrogen. Now, generally, what we do when we have one of these graphs is we try to make a model where we draw a line on the graph and the graph goes through those data points. What I don't think you really need to be an astronomer to see is that the blue line is not a good fit to these red points. There's something must be wrong here. Again, red is the real data and blue is what you get with just hydrogen. And then if we look closely at the individual galaxies, we find that the galaxies are spinning a little bit too fast. If we count up all the matter of the stars and all of the other gas in them, there's not enough gravity to hold them together. They should fly apart like a car losing control when it tries to take a turn too fast on an icy road. And what all of this adds up to is there must be something else in the universe besides the hydrogen we can see and that makes stars. And that must be adding some extra gravity without giving us any light that we can see. So we call this mysterious stuff, well, we can't see it, so we'll call it dark. But other than that, it more or less acts like regular matter, so we'll call it dark matter. And this is basically a placeholder name for something that gives a bunch of extra gravity, but we have no idea what it is. You know, we have lots and lots of theories. There's a huge industry of people writing theories for what dark matter could be, but we don't know what it is. If you were at Renee's talk earlier this week, or last week, she talked a lot about this in her talk. One thing we do know about it, though, and don't worry about what all of these names are, really, this is just saying there's a lot of ideas and we don't know which one is right. One thing we do know is that there's a lot of it. If we, you know, kind of weigh the universe and try and add up how much of the mass in the universe is made up by this weird dark matter stuff, I found there's about 5 times more mass in the dark matter than there is in the regular stuff, the stuff you and I are made out of. And that is just kind of weird. We don't know what any of this stuff is. So that's one of the big mysteries of the universe. And maybe I'm debating if I should pause for a question before. I'll continue. I'll do more questions at the end rather than lose the flow in the middle. Sorry, this is, as with a lot of people, we're doing these Zoom talks for the first time. So there's a little bit of trial and error on the best way to do things. The other kind of big mystery in cosmology is if we look at all of the galaxies that are flying away from us, what we would expect is that gravity would be slowing that down. You know, if the Big Bang threw all of the galaxies out away from each other, we would expect that the gravity from all of that mass would be slowly pulling stuff together. Like a baseball you threw up in the air, you know, it might be going up right now, but you know full well that eventually it will stop and fall back down. However, what we find when we actually measure the speeds of the galaxies, we find that they're actually speeding up. It is literally like we threw a baseball into the air and it kept going up and up faster and faster and faster. Literally what goes up is not coming down. So we figure that there has to be something else out there, something that's making a force that's pushing everything apart, opposite of what gravity would normally be trying to do. Now, what do we call this stuff? Well, it's still dark. We still can't see this stuff. If we could see it, our jobs would be a lot easier. But in this case, it's not acting like matter. Well, we have a word in physics for things that isn't matter. So we call it dark energy. Again, just a placeholder name for weird stuff that we can't see and we don't know what it is. Although, as an amusing little anecdote, you can get grant money out of the Department of Energy because because we gave this stuff the name dark energy. DOE will give you grant money, which is a useful thing for trying to fund large telescopes. Now, I said before, there's about 5 times as much dark matter in the universe as there is regular matter. This dark energy stuff, turns out this dark energy stuff makes up about 70% of the mass in the universe. So this means that the normal matter, the stuff that you and I and the planet and the stars are made of, it's about 5% of all of the mass in the universe. This other 95%, we don't really know what it is, and we are working very hard to figure that out. Sorry, what's being gestured at me? So okay, I have I'll take a question. I'm letting Heather moderate which question should be now or which question should be later. There's a question of if we can't see the entire universe, how do we know that there is statistically that much dark matter? Or also, I guess now, how do we know that there's statistically that much dark energy? That's actually a really good question because it gets into some really deep facts about how we do cosmology. See, there is a idea in astronomy going back to Copernicus, who was the guy who first figured out that the Earth goes around the sun and not vice versa. It's called the Copernican principle, or for us, we kind of upgrade it to what we call the cosmological principle. And what it really boils down to is the assumption, when in doubt, assume we are not special. So we can't see the entire universe. We can't actually add up all of the stars and all of the dark matter in the entire universe and figure out how much of it there is. What we can do is look at the stuff we can see and see how much dark matter there is there. And, we make an assumption that the universe, 10 billion light years that direction, is at least statistically similar to the universe here. And if we make that assumption, then we can get an estimate of what dark matter should be, the total amount of dark matter should be in the whole universe. Now, there's a big industry in cosmology of trying to actually prove that this cosmological principle holds, that the universe is basically the same everywhere. So maybe I can't take beautiful pictures of all of the galaxies 10 billion light years that way. But if I can spend a lot of time with one telescope and maybe see one galaxy and see that it still acts more or less like galaxies here, then that gives me some confidence that the universe is more or less the same everywhere. So it's, at the end of the day, it's an assumption we're making, but it's a very well-founded assumption, and it's kind of core to everything we do in cosmology. Putting it another way, if all of the universe past the moon was just being projected on a movie screen, we'd have no way of telling the difference between that and what we think the universe is. But if we take what the telescopes are telling us at face value, we can have a pretty good idea of what the universe is acting like, even very far away. And actually touching on that point of trying to measure the universe very far away, that's actually a very nice segue. Thank you. I lost Isabel. So the other kind of question in the universe that I want to talk a little bit about is a little bit different. So we have these really nice maps of the cosmic web of the locations of galaxies going out quite far away from us. And we have this map of the universe when it was 100,000 years old. But there's a gap. And that's just because as we go farther and farther away, we can't take pictures of a million galaxies. It just takes too much time and we don't have big enough telescopes. So there's a gap of about 2 billion years or so of cosmic history where we don't have really good pictures of what's going on. We can do math and we can do computer simulations, but in order to do things like prove that the universe is actually the same everywhere, we really would like to see it directly. There's a lot of interesting stuff that happened in that gap. This is when the first galaxies formed, and when those galaxies formed their first stars. This is when most of that gravitational collapse happened that I showed you earlier. And my secret reason for talking about this is that this just so happens to be the part that I work on. And because you are my captive audience, or I guess less captive than you would be in a normal talk, I'm now going to spend my last few minutes talking about the thing that I actually spend all of my time doing. See, so the idea behind what I work on is if I try to make a map of all the galaxies in the universe, Like this is a simulation of one of those over here. Every gray dot might be the position of one of those galaxies, but because my telescopes are only so good, I might only be able to see the very brightest galaxies, which I've marked here in red. Now, if I'm only seeing a few of the galaxies, then I'm not getting the whole picture. I'm not able to, measure the size of these blobs as well as I'd like to, because I only have a few of the galaxies. But, cosmology is built around pictures like this. We don't necessarily care when we're doing this work what's going on in any individual galaxy. My PhD advisor had the slightly derisive term object-oriented astronomy used to describe the entire rest of our field that cares about individual stars and planets and galaxies. But what we say is, okay, if I don't care about any individual galaxy, let's just kind of make take a low resolution smeared out picture of this. So, instead of trying to say there is, a galaxy here and here and here, I say, there's a lot of light coming from over here, and that must mean there's a lot of galaxies here. And stuff's pretty faint over here, so that must mean there are fewer galaxies. And what you can do is, if you kind of look at these pictures, this kind of smeared out blobby stuff over here has a lot of the same cosmic web type patterns as the galaxies over here. So you can, do all of the same physics we do on these really nice galaxy maps on these kind of blobby messes. Whereas, trying to do a map of your galaxies directly would take lots of time on really big telescopes, but we can make these other maps with much less time on less big telescopes, and most importantly of all, spend a lot less money doing it. So one of the telescopes doing this is a project I'm involved in. A lot of us at the University of Toronto are. It's actually the one that's been in the picture behind me this whole time. It's a telescope called COMAP, or the Carbon Monoxide Mapping Array Pathfinder. This telescope is currently trying to make these maps out at an observatory in California. And it is actually still currently trying to make these maps because the telescope can be run without any people there. So even though the university is shut down, the telescope, you'll be happy to know the telescopes are still operating and putting absolutely nobody at any infection risk. So what can we do with this thing once we've made these maps? Well, like I said, the shape and the pattern of these blobs lets us measure the cosmic web, lets us watch this, process of gravitational collapse farther and farther back in time than we would be able to normally. We can fill in that gap a little bit, and we can actually test things like, does the universe still look the same very far away? There's a lot of really fun other things we can do, though. For example, the telescope is called COMAP. I said it stands for carbon monoxide. Now, if you are familiar with carbon monoxide, it's probably because it's a gas where if you breathe it, it will very, very much kill you. That's not really why we care about carbon monoxide. The reason why we care is in those same nebulas where eventually get dense enough to squeeze hydrogen atoms together to make helium, they also take, for example, carbon and oxygen atoms and bring them close enough together, not to fuse like that happens in stars, but enough to make friends and make molecules. And because it's, easier to find one person to be friends with and lots of people to be friends with, carbon monoxide is a very common molecule that forms. And so since these star-forming regions have lots of carbon monoxide in them, then if we can measure how much carbon monoxide there is in the universe, we can see how many stars are being born. And because, again, this telescope behind me, like every other telescope, is a time machine, we can see how many stars were being born in the early universe, much closer to the Big Bang than today. Now, the reason why we can do this is that every atom and molecule in the universe gives off specific colors of light. Carbon monoxide molecules give off radio waves at a specific frequency of, for anybody who cares about details, 115 gigahertz. So just like you might tune your radio to, a frequency of 88.1 or 540 AM, we can take our big radio dish, we can tune it to radio carbon monoxide, we can measure how bright those radio waves are in different places, and we can figure out how many stars are being born in different parts of the universe. And we can actually watch some of the earliest stars in the universe being born, and watch as more and more stars, those stars are born as we approach the present day. And so what this is letting us do, experiments from going back from, Edwin Hubble and Henrietta Swan Leavitt, to the Planck telescopes that took the pictures of the baby universe, to the telescopes that we use to make galaxy maps, to now our telescopes like COMAP. All of this is done through the efforts of hundreds and hundreds of brilliant people over the last 100 years, have let us build up a history of the entire universe from, just a briefest moment after the Big Bang, collapsing down to form the cosmic web, forming galaxies, within those galaxies forming nebulas, those nebulas forming stars, and those stars forming planets. Able to draw a direct line, and again, a surprising amount just due to this process of gravitational collapse, from the beginning of the universe down to the planet we live on. And if I can, to wrap up, if I can summarize very briefly what we've learned from this century of effort, it's that if you take a big enough cloud of hydrogen gas and let it sit for a long enough time, we have empirically proven that you can produce galaxies. Sorry, I should say, this line will not work if I don't start properly. You might have heard, sorry about this. You might have heard the saying that if you give a large enough, this is poor showmanship. If you might have heard the saying before that if you take a large enough number of monkeys and give them a large enough number of typewriters, then just by sheer random chance, they'll produce the complete works of William Shakespeare. Well, by studying cosmology, we have empirically shown that if you take a big enough cloud of hydrogen gas and let it sit for a long enough time, you can make galaxies, stars, planets, William Shakespeare, his complete works, the English teacher that made you read those complete works, you, me, and everything else we see around us today. And that is a brief history of everything. Thank you very much. This is where there would normally be applause, but this is a web talk, so I am just sitting awkwardly. Oh, thank you, Heather. Okay, so I will take some more questions from the chat. I know we had a few while we were going. There's a question from Fahid asking, are there any stars without any planets orbiting around them? So that is still a question we're very much trying to answer. We've only actually very recently gotten to the point where we're able to directly see planets around other stars. We think, and this number is changing daily, we think most stars have planets around them, but not necessarily all stars. But figuring out how many stars have planets around them is still something we're still working on, because it's hard to tell the difference between a star that doesn't have any planets around it or a star where those planets are too small for us to see. So that is still very much an open question in astronomy. Also have a question for Gina, asking how long were the Dark Ages? The Dark Ages, exactly how you define it, varies. But it was probably a few tens or hundreds of million years. That's actually still something we're trying to figure out. Part of the reason why we're building these telescopes, because the Dark Ages kind of by definition end when the first star is being born, something we give the kind of poetic name Cosmic Dawn. And we don't know when that actually happened. There was some people who thought they had measured that recently, but I'm pretty sure their measurement is wrong. But then that starts to get argumentative. So I will leave that for the professionals. We have, oh, this is my kitty who has been, and my wife who has been very helpful, and my kitty who has been yelling for her dinner. She is very cute and very loud. The cat, not the wife. So yeah, that's my talk. Thank you all very much for listening. I hope you learned something. I can leave the stream open for a few minutes if any other questions roll in, but if not, everybody have a good night. Thanks a lot. Cat meows are a necessary evil when working from home. All right. Well, if there are no further questions, then I think I will go off stream. But thank you all for listening. You have been a great invisible audience. And be sure to tune in to the Dunlap website for more of these public talks as we try to entertain ourselves through the indeterminate period of social distancing. Thanks a lot, everybody. Have a good night.